welcome you all on the course of transform calculus and its applications in differential equation. As you know, the transform calculus is basically a technique by which we try to solve a problem we transform the problem from its original domain to some other domain. The advantage is that in the original domain, if I try to solve the original equation, it may become difficult for us to find the optimum solution. Therefore, using these transform techniques, we convert this original problem into some other problem in some other domain, where it becomes easier for us to find the solution of a particular equation. Now, in this particular topics, at first initially we will cover integral transform, and in the integral transform, first let us see the definition of integral transform. Say Kst be a function of two variables s and t, where s is a parameter. Please note this, it may be s may be real or s may be complex also, and s is independent of t. So, we are taking a function Kst, which is a function of two variables s and t, where s is a parameter which may be real or complex and independent of t. The function fs can be defined by the integral like this way. It is f of s, I will show it afterwards also, f of s, this is equals to minus infinity to infinity k of st ft dt, k of st into ft dt. Suppose we have defined like this minus infinity to infinity k of st ft dt, this sometimes we may write as this also, we may write as t1 to t2 also. That means, on some finite domain t1 to t2, or it may be infinite domain minus t1 to minus infinity to infinity. So, if a function fs is defined like this minus infinity to infinity kst ft dt, this is called the integral transform of the function ft, and we denote it by t of ft. We denote this thing by t of ft. So, suppose I am removing this, and if I come to this again, here you see the thing which I told, it is now like this. The function fs has been defined like this way, fs equals minus infinity to infinity kst ft dt is known as the integral transform of the function ft and is denoted by t of ft. The function kst is called basically the kernel of the transformation, and also sometimes we call it as integral kernel or nucleus. So, effectively if you change the value of kst, then we can find out various type of transforms like integral Laplace transform, Fourier transform, like this way. Now, see the input of the transform of a function and the output is another function is small f. So, note this one, the input of a transform is a function ft. Just here if you see capital Ft is the input and your small f is the output of this. Next is a integral transform is a particular type of mathematical operator, we can say. Depending upon the specific choice of the kernel function k, there can be numerous useful integral transform, as I was telling earlier. If I change the value of the kernel function k, I can obtain various kind of useful transforms like Laplace transform, Fourier transform, Hankel transform, like this. Some kernels have an associated inverse which we call as k inverse ut, which we call this one as k inverse ut, and this k inverse ut is defined as ft, this is equals u1 to u2, I will come to this, u1 to u2 k inverse st fs ds. So, which will be a function of s and t, and ultimately you are integrating over s, so that it will be a function of t. In the earlier one it was f s, that was a k was a function of s t, and you are integrating over a function of t. So, therefore, this we are telling as the inverse kernel k inverse we are defining, and from there also we can find out this f t. So, if I go back to my original one, and so the next is f t equals u1 to u2 k inverse s t f s ds, which we call as the inverse kernel, and the last one is a symmetric kernel one, that is unchanged when two variables are permuted. A symmetric kernel one, please note this one, is that one where the values will remain unchanged if we interchange or permute the variables s and t, and if the values remains same, then also we can do the same thing. Now, next come to the Laplace transform. Basically, if you see, your Laplace transform is a mathematical tool, we say. It is simply a mathematical tool which is used to solve various kind of engineering and mathematical problems, and which is used by mostly by the science departments, engineering departments, various departments are using this particular Laplace transform to solve a particular type of problems. This one. This Laplace transform was first introduced by French mathematician Laplace. Laplace transform was developed by French mathematician Laplace in 1790s. Please note this one. This was derived by Laplace, French mathematician Laplace in 1790. Now, this Laplace transform is used to solve ordinary differential equation. In general, whenever we try to find the solution of ordinary differential solution, what we do? We try to find out the general solution, and from the general solution, using the IC, that is initial conditions, we try to find out the values of arbitrary constants. Whereas, if I use the Laplace transform, in that case what happens? Simply Laplace transform converts the ordinary differential equation into an algebraic equation. So, in turn, to find the solution, we have to solve only one algebraic equation, which is basically very easy to find the solution. Similarly, if we try to find out the solution of a partial differential equation using Laplace transform, it reduces the number of independent variables by 1. Since it reduces the number of independent variables by 1, the solution process becomes easier. So, if we go back to this one again, for Laplace transform, then how to define the Laplace transform? If the kernel kst is defined as kst equals 0 whenever t is less than 0, e power minus st whenever t is greater than equals 0. If the function is defined like this, then the Laplace transform of this capital F t is defined as f s equals 0 to infinity e power minus s t into f t dt. So, you have a function f t, the Laplace transform of the function capital F t is denoted by small f s and is defined as 0 to infinity e power minus s t f t dt. So, please note this one, whenever we try to use the Laplace transform, the value of the independent variable t always will be lying 0 to infinity or in the positive side of this one. So, the function f s defined by the equation 1 is called the Laplace transform of the function, and we call it also denoted by Laplace transform of f t or small f s or the capital F s. Laplace transform, as I told, is a mathematical tool which can be used to solve several problems in science and engineering. It was first introduced by Laplace, as I told you earlier, a French mathematician in the year 1790. The method reduces the solution of an ordinary differential equation to the solution of an algebraic equation. So, basically, if I try to solve an ODE, if I apply Laplace transform, then the ODE will be transformed or converted into the other domain, and it will create one algebraic equation. And to find the solution of the original problem, instead of solving the ODE, we have to simply solve the algebraic equation. When Laplace transform technique is applied to an ordinary differential equation, partial differential equation, this will be partial differential equation, it reduces the number of dependent variables by 1. Next is linear transformation. A transformation is said to be linear. Please note this one, this definition we are giving for in general. A transformation, any transformation T you take is said to be linear if for every pair of function f1 and f2 t and for every pair of constants a1 and a2 we have this one. So, linear transformation, if we try to take, this will be equals to T of a1 f1 t plus a2 f2 t. This is equals a1 transform of f1 t plus a2 into transform of f2 t. So, if we write down this thing, so you have a transform t. For this transform t, if we have two functions f1 t and f2 t, if you have these two functions f1 t and f2 t, and if for any constants a1 and a2, transformation of a1 f1 t plus a2 f2 t equals a1 transform of f1 t plus a2 into transform of a2 t, then we say that this is a linear transformation. So, if I have to go back to this, we are writing T of a1 f1 t plus a2 f2 t. This is equals to a1 into T of f1 t plus a2 into T of f2 t. Now, come to the linearity property of Laplace transform. The Laplace transform of a linear transformation, that is Laplace transform of a1 f1 t plus a2 f2 t, this is equals a1 Laplace transform of f1 t plus a2 Laplace transform of f2 t, where a2 and a1 are constants. So, just the linearity property of general transform, what we told just before this slide, same way we can tell that the linearity property of Laplace transform holds if this Laplace transform of a1 f1 t plus a2 f2 t equals a1 Laplace transform of f1 t plus a2 Laplace transform of f2 t, where a1 and a2 are constants. Now, the proof is very simple here. The proof here is simply we know that Laplace transform of f t, this is equals 0 to infinity e power minus s t into f t dt. We know this thing. Now, if we take Laplace transform of a1 f1 t, a1 f1 t plus a2 into f2 t. So, when we are writing it, this equals, using the definition of Laplace transform of f t, we can write it 0 to infinity e power minus s t into this whole term, that is a1 f1 t plus a2 f2t, a2 into f2t dt. So, now I can break this into two parts, two integrals. One I can write down 0 to infinity e power minus st a1 into f1 t dt, that is a1 into e power minus st f1 t dt plus 0 to infinity a2 into e power minus st ft dt. Sorry, this will be f2t into dt. So, this one is f2t into dt, and this is nothing but a1 into 0 to infinity e power minus st f1t dt is nothing but Laplace transform of f1t plus a2 into 0 to infinity e power minus s2 minus st, this is basically your f2t. So, a2 into e power minus st f2t dt, this I can write down Laplace transform of this is f2t. So, this completes the proof that Laplace transform of a1 f1t plus a2 f2t, this is equals Laplace transform of a1 into Laplace transform of f1t plus a2 into Laplace transform of f2t. So, I can remove this, and again we can go back to earlier one. So, just the proof whatever I told you, just I am showing here, so that you can understand it in better way. Same thing we have written 0 to infinity e power minus st into a1 f1t plus a2 f2t, this is equals this, and a1 into 0 to infinity e power minus st f1t dt is Laplace transform of f1t plus a2 into Laplace transform of f2t. Now, come to a piecewise continuous function. A function ft is said to be piecewise continuous or sectionally continuous on a closed interval a to b if it is defined on that interval, and in such that the interval can be subdivided into a finite number of intervals, in each of which ft is continuous and has finite right and left hand limit. The meaning is that a function is defined in a interval a to b, where the function ft is defined and t lies in between a to b. The function may be continuous throughout in a to b, or the function may be piecewise continuous. That means, if the entire domain I subdivide into n subdomains, then in each of the subdomains the function ft will be continuous. Then we call it the function ft as a piecewise continuous function. Say for this one, you have, so this is your defining x, sorry, this is your t, this is your 0. On this side you are defining say any function y equals f x. Your entire domain may be from here to here, a is here, b is here, in between something like that is there, say a to b1, the function behaves like this, this is say a1. From this point b, again it has something like this up to this, then again from here it is coming something like this way, and it is reaching here. So, if I take the entire point a to b, in a to b the function f x may not be fully continuous, but if I subdivide this one into some smaller subsections, say a to a1, a1 to b1, b1 to b2, b2 to b, then in each of these subdomains the function is continuous, then we can tell that the function is piecewise continuous. I hope it is clear that a function may not be continuous in a particular domain a to b, but if I subdivide the function a to b into n subdomains, and if in each subdomain the function is continuous, we call the function as piecewise continuous function. Again, let us go back. So, now come to the other one, that is function of exponential order. A function f t is said to be of exponential order as t approaches infinity if there exists a positive constant real number capital M and a number a and a finite number t 0 such that absolute value of f t modulus of f t less than m into e power a t. So, please note this one, a function f t is said to be exponential order if whenever t approaches infinity, if there exists a positive constant real number m, one a, some number a which is greater than 0 and a finite number t 0 such that absolute value of f t is less than m into a power t, or I can write down absolute value of e power minus a t into f t less than m for all t greater than equals t 0. So, please note this one, that e power minus a t f t is absolute value of this must be less than m for some t greater than t 0, then we say that the function is of exponential order. Sometimes we write this like this way also. So, what we do sometimes, limit t approaches infinity e power minus a t into f t. If this value is a finite constant, if you get for some a greater than, where a is greater than 0, then we can say that f t is of exponential order a. Then we say that f t is of exponential order a. So, in the other way also, as t approaches infinity, e power minus a t f t, if this limiting value is a finite value, then also we say that f t is of exponential order, or we can say that absolute value of e power minus a t f t is less than equals m whenever t approaches infinity. So, we can define it in any one of these two ways. So, these only we are writing. Now, if a function f t is of exponential order a and it is also of order b, please note this one. A function f t is of exponential order a and also it is of order b, where b is greater than a, then we write sometimes f t equals order of e power a t as t approaches infinity. That means, whenever it is of exponential order a and if I know there is a b where b is greater than a, then also we can tell the same thing, that f t is a exponential order alpha, where we can write down order of e power a t. And please note that as t approaches infinity, then only this condition should be satisfied. Example, say we have to show that t power n is of exponential order as t approaches infinity, n being any positive integer. So, what we have to do? We have to find out limit t approaches infinity e power minus a t into t power n, because we want to find out the whether t power n is of exponential order alpha or not, where a is greater than 0. Now, what is happening? This you can write down limit t approaches infinity e power t power n by e power a t. So, that you are bringing it in the form of infinity by infinity. So, once it is coming in the form of infinity by infinity, to evaluate this limit, you can use L'Hospital rule n times. If I use the L'Hospital rule n times, in that case I can obtain this is equals limit t approaches infinity factorial n by a power n into e power a t. So, once we are doing this, after successively we are finding the derivative using L'Hospital rules, ultimately you will get this one factorial n by a power n into e power a t, and whose value this lower portion always goes to infinity. So, that the value becomes 0. The limiting value of this as t approaches infinity always will be 0. Therefore, since limit t approaches infinity, e power minus a t t power n has a finite value 0, we can say that t power n is of exponential order. So, this only I am just showing here. You can just see factorial n by infinity and 0. So, this example shows that t power n is of exponential order alpha. So, I hope now you can understand whether a function is of exponential order alpha or not. For that one, we have to just find out limit t approaches infinity e power minus a t into f t dt. And if the value is a finite value, we say that this function is of exponential order alpha. Next example, you see that so that f t equals e power t square is not of exponential order as t approaches infinity, n being of positive integer. Means the opposite one now we are showing that e power t square is not of exponential order alpha. So, for this one again we have to find out the limiting value, that is limit t approaches infinity, it will be e power t into t minus a. If you calculate the value e power minus a t into f t is e power t square. So, e power t square minus a t, and if I try to find the limiting value of this, always this will be infinity if of course a is greater than 0. So, once I am getting this limit t approaches infinity e power t into t minus a, this limiting value is infinity. So, I can say that e power t square function is not of exponential order alpha. So, simply we can show this, that limit is this e power minus a t into t square, which we can write down as e power t into t minus a for a greater than 0, and the value is infinity. So, by this way we can find out whether a function is of exponential order or not. In the next lecture, what we will study, what is the use of this exponential order or how it relates in the transform calculus. If a function is of exponential order alpha, then what will be the effect, that we will see in the next class.